All right, so in middle school, you guys talked about like taking a shape like this. We called that our pre-image, okay? And then we took a dilation factor of maybe like, let's say 2. And that made that pre-image grow to twice as big, right? Okay? Well, if these are going to be similar, and they are similar, if I go back to like this idea, so I can move them, if I move them both to down here, does that make that angle at B and B prime match up? If I do this, a C and C prime match up, and then we can kind of look at A and A prime match up. So they are similar, okay? But in order for those angles to match up the way they do, that smallest side, that green one's the smallest side in the small triangle, has to match up to the smallest side over here. Does that make sense? Okay? So if I look at, like, let's take BC and divide it by B prime, C prime, and it's going to give me 0.5 back, okay, which is the reciprocal of this, just because the order that I'm comparing it, it's the reciprocal of that scale factor, okay? So it's saying 2.24 is half of 4.47. If I take AB and divide it by A prime, B prime, I should get the same 0.5, and then AC divided by A prime, C prime, I get the same 0.5, okay? Now, as I change this, those numbers are going to change. But if you look at the 3.36s, that means that this one here, if I multiply that number by 0.36, it's going to shrink down to that one, right? Does that make sense to everybody? In order for them to be similar, smallest always needs to match the smallest, because if when I'm looking at similarity, I'm trying to maybe I give you this picture at the onset, and I'm asking you, are they proportional or are they similar? Can you find a proportionality factor? Basically, what you're looking at is an enlargement that has already been done. We just don't know what that enlargement was. Does that make sense? In order to find it, then we need to realize, well, in order to enlarge it without any distortion, without any scaling issues, we need to realize that smallest should always compare to smallest, biggest to biggest, and in this case, then, because we only have 3 sides, middle to middle. Okay. So that's something to think about as we are investigating these types of problems here with side angle side similarity. We'll do this problem here. We're going to do 2 problems like this to ask us, can you determine if these triangles are similar or not? Okay, so give you some information here. A lot of times when they're working with side angle side, the triangles that they provide you are going to overlap. We'll talk why they do that here in a moment. We will be looking at that little triangle there, and then we've got this, it's kind of hard to see, that overall triangle there. So we're going to look at compare the blue one to the purple one. The reason they like to overlap triangles when we talk about side angle side is that we can see right there that angle is angle S, part of the blue triangle and part of the purple one. So they use that reflexive idea to help get that A that is in side angle side. Okay, I like to personally pull these triangles apart. So that's S, that's P, and that's Q. That distance would be 4, and that distance would be 5. And that's a little blue triangle. Then the purple one would be S, and then R, and T. We know this angle S here and that angle S, they are shared, they are reflexive, they're the same angle. What would S to R be? What would that length over here be? How long is S to R? 16. How long is S to T? 20. Okay? So if these two shapes are similar, the smallest side in this one should match up to the smallest side over here. Does that make sense? So 4 to 16 should be my comparison. And that should then equal the largest side over here that I know and the largest side that I know here. So 5 over 20. Now, I'm not saying that 5 and 20 are both the largest sides of those triangles, because I don't know what PQ and RT are, right? So either those are the largest side or the middle side, but it doesn't matter. If these are similar, those need to match up. Does that make sense? Okay. Now, when I cross multiply, what's 4 times 20? 80. What's 16 times 5? 80. Okay. So I get crosstalks that are equal, so those are proportional, right? Okay. So I want to write that triangle SPQ is similar to triangle SRT by side angle side. Okay, now I think there's some other conclusions here that are important to make once I know that those are similar triangles. If they're similar triangles, we should know that angle S is congruent to what angle? S, and that should make sense based on the picture that we have. Angle P should be congruent to what angle? R. And angle Q then to T. Okay? Now, why do we talk about that? Because there's yet one more conclusion that we can make. If that angle right there is congruent to that angle right there, and that's what we said, is angle P. Now, maybe naming it P is a bad choice. It's SPQ. Should be congruent to SRT. You should use 3 letters because P there has multiple angles at P. But those two angles are congruent, and they're also corresponding, aren't they? So what's that tell you about PQ compared to RT? PQ to RT is parallel. Okay? So PQ is parallel to RT in this situation. And that would happen no matter what. Okay? If I'm able to find that the two triangles that they're showing here, no matter where P and Q show up, if I'm able, so maybe P slides down here and Q slides down here. If I'm going to show a top triangle is similar to the entire triangle, that will guarantee that PQ is always parallel to RT. Okay? Another thing that is nice, essentially a conclusion from that, is if you know two triangles are similar and they're overlapping like this, you automatically know that the sides that look like they're parallel are indeed parallel. Does that kind of make sense? Okay? So if I were to give you maybe a picture like this where we have those two triangles, and I tell you that this top triangle is similar to the overall triangle, that automatically then tells you that that segment there is parallel to that segment there. And that's a feature that this last couple sections of this chapter will actually kind of dive into and allow us to maybe generate some other proportions that we can deal with, okay, from the information in those triangles. Just kind of maybe doing that real quick. What that will lead us to, what is 4 compared to 12? What's that reduced to? 1/3, right? What's 5 compared to 15 reduced to? 1/3, right? Okay? And that comparison is because we know that those are parallel. Okay? Take a minute and see if you can figure out which two triangles there are similar. So I want you to give me a similarity statement. And then I want to know your logic. What is the essentially scale factor or value of that proportional factor when we do this? So I'll give you a minute to do that. All right, so when we look at that triangle right there, okay, they tell us that little triangle is isosceles essentially, right? Through the use of FG is congruent to EG. And if it's isosceles, that means those two little angles that I colored down there, red and purple, should be congruent to one another, right? The base angles of an isosceles triangle are congruent. So if we do that, now I'm going to pull these two triangles apart. I think that makes most sense in trying to decide on what I'm going to compare to one another. And when I pull those apart, my purple angle is right there and my red angle is right there, and they should be congruent. Okay, so that's the angle that if these are congruent, or sorry, similar by side angle side, that A is the red angle and the purple angle. Okay, so then the sides that sandwich those angles are 9 and 15 and 12 and 20 respectively. If they're similar, what should 9 compare to? 12. So then 15 should compare to 20, right? Okay. When I cross multiply, 9 times 20, 180, right? 12 times 15, 180. So those are proportional. Some of you might be, well, I like to divide both these by 3, and that gives you 3/4. Both these divide by 5, so again, that gives me 3/4. Okay? Another way to say they're proportional. But that being said, now I want to write down the name for these. I'm just going to name my first one ABE. Okay? If I name the first one ABE, then I need to name the second one, so we'll say it will be DCF. Does that make sense? Okay? Now, if you named your ABE differently, maybe you went BEA, then we need to name this one CFD. If you named it BAE, you would need to name this one, what, CDF? Okay, and there's some others you could do. But that would be a series of our similarity statements that we could create, right? Now, the question is that I'm going to ask, because eventually this is going to be important. Eventually they're going to give me like an algebraic expression for angle A, an algebraic expression for angle B, an algebraic expression for angle C, and an algebraic expression for angle D. Okay? And I'm going to need to relate two of those to one another so that I can get an equation that is accurate. Does that make sense? Okay? So what would angle A? Angle A is going to be congruent to what angle? We're using maybe that similarity there. Angle A is going to be congruent to angle D, right? Okay? So when they give me like this expression there, and I have to decide, do I make it equal to that one, or do I make it equal to that one? It's now telling me you got to make it equal to D, right? And then you can set up the correct relationship so that you can solve for a missing value. Okay? So that conclusion, obviously, we like to say, yes, they're similar, but we can go further with that and say, okay, now that we know they're similar, there should be a series of angles that we know are congruent to one another. Okay? The last one we're talking about is side-side-side similarity. Okay, and all this means is that if you can compare all three sides to their corresponding sides, and they divide to give me the same ratio, meaning they're proportional, then that's enough to say the triangles are similar. You don't have to worry about the angles. Okay? Once I say they're similar, the conclusion then, what I gain from that, is that the angles are indeed congruent. But to get to there, all we need to know is that the sides, all three sides, are proportional to one another. Again, this is a situation where if we don't talk about comparing smallest to smallest, largest to largest, middle to middle, you might have to go through a lot of work to kind of decide whether these things are similar or not, okay? So that's the best thing to do. If they're going to be similar, we understand that dilation aspect. So we're going to compare smallest to smallest, largest to largest, middle to middle, and see if they divide out to give me the same ratio, okay? What they're doing here with this picture is that like A would compare to AX, B to BX, and C to CX, okay? Meaning X could maybe be like a 2 or a 3 or 4, whatever, and it just takes A and doubles it or triples it or whatever. But when I look at these, do they all divide? Does A and the A over X, do the A's cancel out? And the middle one, the B's cancel out, and the last one, the C's cancel out, so I'm left with 1 over X equals 1 over X equals 1 over X, and that's the argument that those must be proportional because that ratio is the same, okay? So if X was 3, we'd get like 1/3, 1/3, 1/3. If X was 5, we'd get 1/5, 1/5, 1/5. Does that make sense? Okay. That's when I was showing you this earlier, that's where we're getting, so if that was like a 2, that's where we're getting 1 over 2 here, okay? If it was 3, that's where we're getting 1 over 3 here with those, okay? Scroll down, do these examples. So this first example is not too difficult. They're just asking, are they similar? Okay. So the information provided is going to tell me to compare sides. So this is if they're similar. The only way I can do it, I don't know any angles, so I'm going to go side, side, side. So then I'm going to start looking at my objects over here, my side length. So if I compare like 10. What should 10 compare to over here in this figure? 15. So that was biggest to biggest, right? So I've used 10, I've used 15. Maybe I cross those off just to eliminate any confusion later on. What should 8 compare to? 12. And that leaves the last two to compare that way. Okay. Now you can, I don't like doing that. I'm not a big fan of reducing and saying, okay, these both have a factor of 5 in them, so I can reduce that to 2/3. These both have a factor of 4 in them, reduce that to 2/3. These have a factor of 3, reduces to 2/3. And you can see that those are all the same, so then these are proportional, right? I like this, just a personal preference. I like to look at those two and just cross multiply. I feel like I can cross multiply. And these numbers aren't too bad to do the division. But if they were decimals or they had irrational values or whatever, or they were symbols like AX and A in the description earlier, I want to use cross products. If I cross multiply there, I get 10 times 12 is 120, 15 times 8 is 120, right? Okay. The next thing I do is then I look at the last two. Okay, the 8 twelfths and 6 ninths. So if I go 12 times 6, that's 72. 8 times 9 is 72, right? So the last two are equal to one another. That automatically tells me that that one and that one should be equal to one another because that 8 twelfths was the link between the green ones and the blue ones, right? Okay. So that means 10 15ths should equal 6 ninths. If I cross multiply, 15 times 6 is 90, 10 times 9 is 90, and it validates that. But I don't need to do that multiplication because the transitive property tells me it's going to be true anyways. Okay. So those would be similar. All right, so I'm going to write a similarity statement. Okay, so maybe I call this triangle STU. If you call that STU, so I went down the small side and then the middle side, right? So over here I need to go from X to V and then finish at W. And now you would be able to tell me which angles are congruent in the event that we need to. Does anybody know what kind of triangles, beyond being similar, does anybody know an additional fact about those two triangles, what they could be, or what they are? They're right triangles, okay? Because they abide by the Pythagorean theorem, right? If I take 6 squared, I get 36. Take 8 squared, I get 64. Add 36 and 64, you get 100, right? 100 is equal to 10 squared, which is your C there. If we go A squared plus B squared equals C squared, okay? Does anybody know? So same thing happens with 9, 12, and 15. Then if they're similar, then that must be a right triangle as well. Anybody know what kind of numbers as a group we call those? If they're whole numbers that abide by the Pythagorean theorem, like 3, 4, 5 is the smallest one. 6, 8, 10 is one from that. 9, 12, and 15 is a set. I think 5, 12, and 13 is a set. They're called Pythagorean triples. Okay, Pythagorean because they work for the right triangles because of Pythagoras. Triple because there's 3 of them. Okay, 3, 4, 5 is kind of the foundational Pythagorean triple. It's the Pythagorean triple that has the smallest possible side length. This picture. If I'm going to say that these are similar, can I use side, side, side? Do you know all 3 sets of sides? You don't, right? But if I look at these, do they both have K in them? Is K in the small triangle and in the big triangle? So that's an angle that we're aware of. Okay. Now, if I want to use angle, I would need another angle, right? I would need another set of angles. Do you know if that angle there is congruent to that angle there? What would I need to know about that line and that line if the green angles are going to be congruent? They would need to be parallel. Now, they look parallel, but there's no notation in them to tell me that they are. Okay? So I can't use angle, but I do have some side lengths here. So maybe we could use side angle side. So what would K to P be? 12. K to M is, I mislabeled that point. It's KL. K to L would be 8, right? K to M is 10. K to N is 15, right? Okay. So if these are going to be similar, shouldn't 8 compare to 10? Like 12 compares to 15? Cross multiply, I get 120 there. Cross multiply, I get 120 there. So I can say that triangle KLP is similar to triangle KMN. And now the thing is, if I told you what LP was, you should be able to tell me what MN is. Now that we know that they are similar triangles, now you can make the argument that that is indeed parallel to that. Okay. What is nice about this feature is that eventually, guys, so if I were to give you, let's say, and then, like I said, this is what's going to happen later on in this chapter. If I were to hide that 2, and I were to put X there, L to M is X. Okay, and I give you all that information, that picture that's currently there, and I ask you, can you find X? You can do one of 2 things. You can do what we just did, okay, where you say, okay, well, 8 should compare to 8 plus X, just like 12 should compare to 15, right? That makes sense? If I cross multiply there, I get 8 times 12 is, what is that, 92? Sorry, 96. 96 plus 12X is then equal to 120. Okay, subtract 96, and I get 12X is equal to 24. So X is 2, right? Does that make sense? Or, what actually ends up being easier, and it's because of this idea now that we know those are parallel, I can actually say 8 compares to X, like 12 compares to 3. Now I cross multiply, I get 24 is equal to 12X. Is that a lot easier to get X to be 2? That kind of makes sense? So it allows me to create a comparison between those 2 distances on that side of the triangle and then the 12 and the 3 on the other side of the triangle. Okay? But that principle stems from what we're able to do with the 2 overall triangles and their similarity. We'll stop there for today. I'll give you some time here to work on the 7-3 assignment. That worksheet that I gave you that had the story problems on it that we went over yesterday, or we talked briefly about each one of those questions on there. That will pop up at some point tomorrow. I had it planned for today. I made it, and now I'm trying to assign it, and it's gone. It disappeared. Okay, so I don't know if it didn't save or what. So I've got to recreate that, but that will be open at some point tomorrow. So keep working on that. If you do not have that finished, we'll collect those answers tomorrow at some point.